welcome to the panel. I'm going to moderate this panel. Looks like it's going to get pretty rowdy. We'll introduce the speakers, the panelists, and maybe ask each of them a question, but of course any other panelists can weigh in on these questions. First, we have at the right Philip Hennig from Max Planck. Philip, I thought if you could venture to tell us a little bit for a moment about probabilistic numerics and maybe the role of approximate inference, either to help or as probabilistic numerics to help with approximate inference.
So it was a strategic mistake to sit on the far right to start this conversation. Since probabilistic numerics hasn't been mentioned at all in this workshop, which is completely fine, maybe I should spend 2 minutes maybe very briefly outlining. So there's a sort of a very old idea that has been around in statistics and applied mathematics for the past 100 years or so, since Poincaré, that it's possible to think about computation as such as inference, because a numerical method estimates something you don't know, like the value of a normalizing constant of a probability measure, given things that you can know or compute, like the value of the density at various points. So these are numerical algorithms decide to perform certain computations, which return something you could think of as a data point, an evaluation, and then try to construct estimates from that. And so in recent years, it has become more and more clear that actually it's possible to make this connection. It's a philosophical idea quite close. So many classic numerical methods are, in a specific technical sense, least squares regressors or Gaussian map estimators. And so now the interesting question is to which degree it's possible to make use of the Bayesian interpretation of this sort of connection. So to which degree does the associated uncertainty measure of these computations actually mean something, and can it be used to build new methods? Okay, so that's the general idea. How is this connected to approximate inference? So far, there's been very little work on this, and I think it's actually a very exciting question, how this is really good. And I'm tempted to say that's the entire answer, right? Because there's actually been very little work on it. So classic variational norms, of course, can in some sense be seen as performing regression in a non-Gaussian way, right, under a different loss function. And the loss function is like divergences. This has not really been sort of turned into a probabilistic framework. But I think this is actually a really exciting.
So, yeah, I was just going to jump into that. I'm surprised that you didn't articulate a connection, which is that a lot of Bayesian computation is integration, and sort of quadrature is a big part of what sort of you guys have been up to. Have you found? I mean, well, it seems like it could be very interesting, both in terms of sort of improving rates, but also actually representing the uncertainty associated with Bayesian computation in a way that might not be available to other methods.
Yes, so Bayesian quadrature is a really exciting direction for approximate inference. That's absolutely true. So I'm not sure whether Mike Osborne is still here. He's been sort of working in this direction, probably with various other people as well. I think so far we have really not seen yet the potential power of Bayesian quadrature in approximate inference. And that's partly because these methods are much younger than MCMC, so there's still many really open questions. On the other hand, we also do know that MCMC has some fundamental problems. And this has been known since at least Tony O'Hagan in the 90s, right? So it's a fundamental problem of MCMC methods that they are not self-avoiding, so they're sort of problems with diffusion, and we've seen some talks today that try to address this. Bayesian quadrature is one formally quite elegant way to address this in a very sort of specific sense, in the terms of actually using uncertainty measures to decide where not to go back to. And this can be sort of formulated in a very powerful kind of language. But of course this comes with downsides like higher computational costs, which so far have not been addressed particularly well. So I don't think I think in the long run it would be very interesting to see whether it's possible to make numerically more precise statements about the kind of quantities we're trying to estimate with something like quadrature. And so far, we're lacking some of the sort of algorithmic details. I think actually the theory is really beautiful, and the algorithms are not quite there yet.
Thanks. To the left of Philip is Ryan Adams from Harvard University and other entities. Ryan, so you're one of the experts who's had extensive experience both with MCMC, but they're in the hot seat, by the way. I didn't tell anybody which question I'm going to ask them, so you can see Brian kind of tensed up. And I'm excited to ask this question because I usually am on the receiving end of this question. So, Ryan, you've had extensive experience with both MCMC and variational inference. You've done applications, deep galactic applications with both. So, what advice do you have for approximate inferencers who have a new problem and are trying to decide? And what kinds of considerations and rules of thumb do you use when you're solving a new problem and trying to think about what approach to take to approximate inference?
This is a really good question, and I feel like 10 years ago there was like a very distinct difference between problems that you might solve with variational inference, in particular mean field type algorithms, and things you might solve with MCMC, where what we would always talk about is this difference between, do I want an algorithm where when I spend more computation I get to I eventually get to a better solution, or do I want to get to a worse solution faster? And at the same time, questions about, on the mean field side, how much do I care about sort of higher order marginal computation? And mean field might lose track of those, but if you only care about sort of lower order marginals, then that's not a big deal. But the truth is that these days, it's all over the place now, right? Like variational inference now, with stochastic variational inference and black box variational inference, a larger class of models are now possible to fit with these tools, at least in principle. The existence of automatic differentiation has sort of, in addition to raising the tide of deep learning, has raised the tide of variational inference for these black box methods, as well as things like Hamiltonian Monte Carlo, where methods in probabilistic programming and so on that you might never have thought of applying HMC or variational inference to, recently, suddenly now these things have become possible. So I think to some degree this distinction is really fading, and I personally still like to do I will still tackle the problem with MCMC quite often, but that's largely a function of the sort of like workflow rut that I've gotten into in my personal career. But my students are who don't have such deep ruts are quite happy doing both of these things quite often, and I think it's also clear that there's been a lot more interchange between these areas. I think mean field variational inference, if you're only going to care about marginals, is still probably the first thing to go to. I continue to like the joke that you derive your variational approximation while you're waiting for your Markov chain to mix. And I think that still kind of holds true, but just less and less every day. I mean, tools like Stan and so on are now just, they're really amazing. And so this is just such a less interesting question now than it was like 10 years ago. but that's a great thing, right? That's like an amazing property of this community that everyone has learned from each other, and that these tools that have been pulled in from other areas as well have sort of made it possible for this to not be an intellectual choice so much as a kind of like, what's the right tool for the job today choice, which is exactly where we need to be.
Yeah, I'd like to weigh in there, because actually approximate inference keeps me awake at night. Like, I'm really happy explaining to students that with Bayesian decision theory we can separate inference from decision making, and then you do a nasty thing halfway through the course where you move on from Gaussian tractable models or discrete models. You say, now we're going to do approximate inference, and now that separation of approximate inference from the actual decisions you're going to make with your posterior is no longer valid. You really do need to think about what actually your task is that you're interested in. And so I'm really personally really worried that we don't have a fantastically fine-grained understanding of the interaction between the probabilistic model that you want to do inference in, the loss function on the task that you're interested in, and then sort of other concerns to do with how long you have to compute these things. And so, in a sense, I see I guess my research agenda, and I guess the research agenda in some sense of this community, as sort of answering that question, like speed accuracy trade-offs for models and particular classes. And these things do have a big effect. So, for instance, speaking from our own work, the difference between running EP and variational methods, EP can give you well-calibrated uncertainty estimates, which are way better than variational methods. Variational methods tend to give you back better mean squared error estimates and better classification accuracies. And that then opens up sort of, as we compose approximate inference together, and lots of the talks today have been about composing Monte Carlo distributional approximations and so on and so forth. That space then becomes a really hard one to navigate and give cogent advice to people who aren't perhaps as expert as some of the practitioners here in using these methods. So I think the question is now more complicated than it used to be because they're all competitive with one another.
Yeah, so I guess I should say that I'm not asserting that approximate inference is solved, just but that all the methods are starting to share a lot of the same methodologies, right? And this is a different situation than it has been, where the methods have very distinct pathologies. I think we're seeing a sort of these things come together. But I totally agree. I think there continue to be sort of very serious open questions about this balance. I mean, there's a kind of I feel like there's a spectrum in inference, broadly speaking, right, between a world in which you tend to specify the model that you really like, your favorite model that has all the details built into it, and then you're going to have to, but now you're going to have to use an inference algorithm that is really probably not going to work that well and that you're not going to trust, and you're going to hope it's going to work out fine. And then at the kind of the other end of the world is I only look at model, I turn whatever model I want to have into a model that I can solve with like a semi-definite program. And then there's a bunch of stuff in between these areas, and I think this is exactly kind of what we're seeing is how do we rationally make that trade-off where we give away pieces of our model in favor of inference algorithms that we understand better.
That was an interesting answer to a non-interesting question. Next is, the plan is not to have a discussion and then I make a joke, and then, but it seems like that's what's happening. Yeah, that's right. Next is Barbara Engelhardt. She's a professor in the computer science department at Princeton, where she straddles machine learning and statistical genetics. So Barbara, your talk today and also other talks, I'm thinking of Jeff's talk too, was about using models to do science, like real science. And you've had a lot of experience with this. What are some of the challenges to, we just talked about approximate inference and all the ways that different methods fall short or are good. Not only that, but the model is also usually a simplification, as Ryan pointed out, by necessity. What are some of the challenges to using this methodology to do science, both from the perspective of doing science, answering questions, but also from the perspective of communicating the results to scientists?
Yeah, so I think a lot of my answer is basically echoing what Ryan just said, but the real problem with the kind of scientific data that I look at, I think Jeff's problem is slightly different, but I have really limited number of samples. So I am really in the situation where the number of samples that I have N is much smaller than P. P is gigantic, 20,000 in the example you've seen today. You've worked with genomic data, Dave, and you know that they can get up to 4 million features that are all very well correlated, that have a lot of structure. And to be able to actually pull out signal in those data, you need to have these very, very rich and complex models. But then you run up against this problem of not being able to actually do inference in those models. So, in my group, we really start with the easiest thing. So the model that I showed you today was really born out of us just trying very, very simple sort of L1 regularized sparse factor analysis, and then we had to keep building and building and building until we could actually pull the right signals out. And then because we had to keep building, we had to keep developing, or not developing, but just generating the different approximate methods to solve the problem. In terms of communicating it to scientists, then I think it goes back to, again, some things that have already been said here, but really putting error bounds on it, describing the robustness. I feel like every paper we submit to a genomics journal says, what happens if you run it 1,000 times? Do you get the same answer every time? And the robustness is really a big issue in confidence bounds as well. So I guess the thing that you saw today from the work that we did is really the question is how do you validate, especially in these exploratory models. LDA was another model that was discussed. How do you validate what you're finding? And there's no real null hypothesis or no way to evaluate the quality of the result. What would happen if the data didn't have a particular pattern? Would you still get something that looked like that? And I think it's a really difficult thing to convince people who are scientists who are used to seeing these statistical tests that this sort of unsupervised learning is doing the right thing without actually validating it.
I didn't actually say yes, but I kind of look sufficiently interested. So I think this is really interesting to see this kind of moving target of how, as our community is building these more and more complex models, the computational demands are rising as well. And I think at the moment we're maybe at a point in time where arguably our progress as a community is actually hampered more by the computational problems than by the modeling problems. We have all these exciting models, and we could all these super exciting things if only we could do the computations a little bit better. In particular, if you're not working for a company that has infinite computational resources. And I think that's why, so that people in this room are actually at a really exciting place, right? Even though it might right now seem like there are other areas of our community are more popular at the moment. This is going to be a really exciting time to think about computation as well. So computation is sometimes seen as a boring part of our field maybe, or generally of any sort of applied mathematical field, but it's actually beginning to be really important for machine learning, that we build better numerical algorithms. And then as they become more reliable, we'll be able to build more complex models again and do cooler analysis.
Okay, thanks. Richard Turner's from University of Cambridge, and my question for you is about divergence measures. So, a lot of the talks today worked, at least around variational inference, worked with KL divergence, and we know that we enjoy, or I should say I enjoy working with KL divergence QP because it's stable, it's easy to compute with. I know it has problems, I learned about them from you. But many optimization methods are straightforward in that context, and of course it has limitations. So can you comment on alternative divergences, if you think they're important, why you think they're important, how to choose, and anything else you might want to say about that subject?
Great. That's a great question, and I think a really important question. So I came into Approximate Inference from a neuroscience side, so I was looking for algorithms that I thought the brain could implement in order to do probabilistic inference on what's going on in the world. And one of the first things we tried was variational methods, and I was disappointed by how well they performed. So in particular, one of the sort of pathologies which a lot of the practitioners here will have experienced with variational methods is that they overprune. So they give back models which are more simple than the actual true model that would have generated the data, if there is such a thing. And so this is an inherent pathology with variational methods, especially if you initialize them in a bad way. We saw it in Matt Hoffman's talk when the model was pruning out a whole load of components. And it's sort of intrinsic to the particular variational bound, because you have a bound which is log marginal likelihood, the true log likelihood minus a KL divergence. The optimizer can either give you back hyperparameters that optimize the log likelihood, or it can put the hyperparameters in a particular part of the space where the KL goes to zero, i.e. where your variational approximation really is a good approximation for the posterior. And that often happens when your model just gives up on the data, because then the parameters just sit at their prior, and the KL distribution goes to zero. So variational methods tend to give up on the data, and therefore give you back much simpler methods, simpler models than the ground truth. So that's one thing that really bothers me. Another thing that bothers me about variational methods is they tend to be overconfident as well, which for many applications like probabilistic numerics, I can imagine, or Bayesian optimization, things like this is a bad thing to have. So the question is, what can we do about it? And one natural thing to do is to consider other divergence measures, and possibly that will give a way out. So our group spends a lot of time working with EP, and one of the pervasive misconceptions in our community is that EP is a bit like variational methods, but with the KL the other way around. And that, maybe if I say it here loud enough, That is totally not true, and it's totally not the justification or the reason or the goal of EP. EP instead is an algorithm which locally applies KL divergences, which can be the other way around, at the level of different factors in your approximation. So there are two differences between expectation propagation and variational methods. One thing is it does use the KL the other way around, and secondly, it's a local algorithm rather than a global algorithm. And there's an awkward interaction between how you write down your model and so sort of the factor graph describing your model and the EP algorithm. There, if you choose a different factor graph for writing down your model, you'll end up with a different EP algorithm. So one big picture take home is if you write down a factor graph which is very localized, you'll end up doing something which is more variational when you run EP. And if you write down a sort of more coarse-grained factorization, you'll end up doing something which is more like global KL P to Q, the other way around. So that means it's not straightforward to answer questions about what are the properties of EP, and there are papers here that are trying to do this. Okay, what's my general advice for how you do this? Or for how we might choose between these different divergence measures and these different algorithms. So one thing is, if your loss function really does care about uncertainties, you should be more like EP, more like KL P to Q than variational. Variational gives poor uncertainty estimates out. If you're interested in hyperparameter optimization, things are tricky because hyperparameter optimization in EP is a bit more complicated, but it's potentially the case that these biases, which are inherent in variational methods, are a lot less severe in EP, although it's a little bit more difficult to do hyperparameter optimization. Other things which are true, if your model contains non-smooth potentials, so things like step functions, delta functions, or a classification likelihood which is from a well-separated class, so it's very step-like, then don't do VB, you should do EP. It will do much better on non-smooth potentials. And so the third sort of general big take-home is if you're doing factorized approximations, then in a message passing context, it's generally the case that EP will outperform VB because of this uncertainty issue as well. So it's hard to give, as you can tell, my answer is, I could go on about this for 45 minutes or something like this. It's a bit of a subtle list of things which are relevant at different levels of the problem, cascading down from the loss function to things like to do with hyperparameter optimization. But suffice it to say, for a large number of models, I would use VB, and for another large set of models and cost functions, I would use EP, and we should be devoting research resources into coming up with perhaps less garbled advice about when to use one of these things.
Thank you. Anybody else have comments on Divergences? We're getting a maybe from Philip. All right.
It's coming, Fred. So this is a little bit meta on this, but that's maybe actually summarizing all of the sort of a point that was sort of between the lines in all four of our answers, is that there is this question of reliability and being able to make statements about how reliable a computation is. So this is, I had to start very carefully with my introduction on Bayesian quadrature, and I basically had to say, well, it's not really there yet, right? But this is one area where Bayesian quadrature really gives the right answer. So the wonderful thing about Bayesian quadrature is that it's least squares regression. So the entire wonderful world of statistical learning theory comes and helps us in error analysis. So we know that if the log likelihood lies in an RPHS that is reproduced by a particular kernel that we use for Bayesian quadrature, then the method is quite consistent. And in fact, there are stronger results that say if there is a particular kernel, like polynomial kernels, and your log likelihood has a certain number of continuous derivatives, then the associated error estimate of Bayesian quadrature is actually an upper bound on the true error. So really strong kind of statements of, if you use this error estimate, this Bayesian error estimate that comes out of the computation, is reliable. And this can be used as a sort of a sense of model guarantee, right? Now, why are we not all doing this? Because unfortunately, it only works in low dimensions. So I would like to add to your list. So among all the other things you said, and if your model is actually low-dimensional, just use quadrature. Which is a really silly, so simple kind of thing to say. It's totally obvious, right? If you have a two-dimensional thing, just call quad 2 or whatever your favorite language calls this sort of operation, right? And I think this is sometimes sort of a little bit ignored, just sort of aside. We're hoping that eventually, in a few years' time, we'll be able to make these kind of statements for much, much higher dimensional problems as well. But right now, this is already true, and of course, it's not a new result. Right? This is something that the American mathematicians have been doing for a long time, and that's also why they care so much about quadrature, because it actually has error guarantees, and it's consistent. It converges with known grades. So this is something that's totally lacking for the other approximate inference methods, except for FCMC. But you know.
Yeah, I mean, I just to follow, I totally agree with that. One of the beauties with EP is that it does break a complicated high-dimensional problem up into a series, often of local approximations where you can apply something like quadrature. So maybe a synthesis of the two, which people have looked at, is a sensible way forward. And I'd just like to echo the view that, at least my own peace of mind, I think more theory associated with all forms of approximate inference, and perhaps especially distributional inference, would make us rest easy at night. Like we don't really have a defensible position for people to say that this is the way forward until we do have either empirical, a huge body of empirical evidence, or some theoretical guarantees of some description or other, which probably have to involve a loss function in that for sort of guaranteeing that these things are sane.
We have more questions here, but I wanted to open it up to the audience. If anybody has a question, there's a lot of expertise here behind the table that you want the panel to discuss. There are no questions. Okay, I have another one. Oh, yep, this one.
Sorry. So this year, I think like the idea of like deep networks with the Bayesian paradigm has been taken off the scenes, and I'm part of the reason. Problem with Bayesian inference is when a model somehow does not fit the reality so well. The deep networks are encouraging for that because they can supposedly fit anything as long as you have enough layers and enough parameters. But how, we're drifting into a dangerous land, right? Deep networks are also kind of not so well behaved, they get multiple modes of sphere, stuff like that. So I'm just curious to know what the panel thinks about this combination of deep nets and Bayesian.
Okay, for those of you that didn't hear, the question's about Metropolis Hastings. And the question is about what the panel thinks about the combination of deep nets and approximate inference.
So let me first just sort of say something about the last thing you said, which is now that we've introduced deep networks into Bayesian inference, now it's all miserable and our postures suck. But that was true before, right? I mean, for all the interesting things that we're doing, for many years, right? These postures were hard to manipulate, and this does make them harder for sure. But I'm not sure that it's like a step change in how hard they are. I tend to view deep learning through the somewhat unglamorous lens of adaptive basis function regression. And function approximation is a great idea, right? And having a rich space of functions in which to do those approximations is obviously wildly successful. But I don't think it's that different in some ways than inference problems we've been struggling with for a long time. In terms of sort of excitement around this, I can tell you why I find it really exciting. It's because we want to use the best tools for the job, whatever the job is that we're tackling. And a lot of times the best tools for the job are graphical models, and other times it's deep networks, right? And graphical models, I think, in some ways, it's easy to forget just how incredibly, wildly successful they are, because they're in some ways in the background for so many things. So Kalman filters, like, if you've got sensors on your phone or whatever, like right now, they're probably using some kind of Kalman filter to smooth that signal out in order to estimate your accelerometer or whatever it is. You've got, HMMs are obviously built into tons and tons of different things. Error correcting codes that enable your Wi-Fi to work. I mean, some of the best decoders for these things are based on the idea of belief propagation. The list goes on. Like, there's a very, to say nothing of things like say nothing of things like mixture models and so on. So, graphical models and inference in these things are some of the best stuff that the sort of broader machine learning community and statistics communities have created. for signal processing and lots of different problems. And then deep networks are obviously now very, very good at high-dimensional classification problems, discovering structured features that can then be reused and composed, and they're increasingly interesting for high-dimensional density estimation. And so what I think is exciting about this kind of emerging area is trying to ask these two different tools to play nice together and each of them to solve the problem that they're best at. And in the work that, like, for example, Matt Johnson has done on structured variational autoencoders, it allows you to wind up with interpretability of the structure you're discovering in a way that a big recurrent network by itself might not be capable of doing, but nevertheless have the flexibility and power of these function approximators to not have your likelihood just be completely owned by the by the sort of by the pixel data, for example. That is to say, if you've ever fit a mixture model to interesting high-dimensional data, then almost always it's not a question of kind of how many mixture components you have. It's that in high dimensions, if you're Gaussian or whatever it is that your component densities are going to be a horrible match to the data. And so trying to fit one of these things can, in addition to just being very difficult, you can wind up with a very large number of uninterpretable components simply because the model is trying to fix up this density mismatch. By throwing a very flexible neural network type model into it, then you can fix that up at the component level, right? And by fixing it up at the component level, then that sort of relieves the burden on the assignment of the components themselves to maybe yield something that you can now kind of understand. And that seems to be true not just for things like mixture models, but also for other kinds of structured models that we like to use.
There's a workshop tomorrow, you probably know about it, on Bayesian deep learning, so that might be another place to talk about this. Yeah, good question.
So I wanted to ask Philip and Ryan, your supervisor taught you in physics PhD that you have to write down the probability of everything through some logic. And now we see workshops again. What's your thoughts on that?
Well, I know David as well, or knew David as well, so maybe I could come in here. I think there are a few things to say about this. So one thing I think we need to develop are suites of tools for assessing the quality of probabilistic models. And they might be probabilistic models which are trained using adversarial training, or they might be variational autoencoders, or they might be some other type of probabilistic model. And we don't, as a rule, do enough detective work investigating how well our algorithms have performed at training the models that they spit back to us, especially in the sort of the NIPS culture where you have a relatively short paper and you need to provide a bottom line number and move on. We don't really do forensic analysis of that would be required in perhaps a stats journal and should be required, in my opinion, at NIPS to really figure out what's going on. So one of the tools which is available for us that helps, I think, is generative models, being able to generate data from a synthetic model where we know the ground truth, and we can test how well we can learn the parameters or do posterior inference perhaps in those models. And I guess I'd like to plug Roger Gross's work here, actually. So Roger at this conference has a really neat method for from synthetic data generated from a synthetic generative model, being able to bound the true marginal likelihood of that model. And then you can test the efficacy of various inference schemes on that synthetic data, so things like GANs, which he's tested, variational autoencoders, methods trained using the importance weighted autoencoder and things like that. So one of the messages which comes out from that is that, which I think is sort of fits with the folklore here, which is that GANs use their parameters to model data in a relatively small part of data space. They sort of devote their modeling effort to a relatively small region of images and can give you really high quality samples of things in that space as the data space. Whereas if you train things using a variational autoencoder, it tends to spread its probability mass more diffusely over the actual data distribution. So you actually, if you use things like the marginal likelihood estimates to estimate the quality of these methods, the variational autoencoder is actually doing better in terms of NATs than the GAN, but the GAN is producing nice, pretty images which look a lot better in general. I think, this is a bit tangential from your question, but just to make 2 points. Firstly, I think we need to develop more tools like that let us go in and, we do lots of fine-grained experiments where we know ground truth and try and actually understand what the properties of these inference algorithms are, what their strengths and weaknesses are. And secondly, I think we should embrace these new ideas, and use those ideas inside the context of approximate inference. GANs do not do inference, but you could train the model parameters using a GAN and then develop a variational autoencoder to amortize inference in those parser models as well. So I think that just adds to our toolbox of interesting options for inference and learning.
Maybe coming back more directly to the start of your question. So, as Ulrich, of course, as you know, David spent a part of his academic career trying to come up with Bayesian interpretations of neural networks. So, if your questions are, of course, a little bit in this direction of, so should we all stop being Bayesian because everything is deep now? I think, for me, David was actually a great example of staying, yeah, of course, yeah, sorry, lots of Davids, yeah, David Mackay, of this sort of conviction that we really need to understand probabilistic interpretations of our models, even if they're already out in the wild and are being used. And I've sort of inherited this sort of zeal from him and sort of tried to use it now in the context of computation. And so why do we have to do this? Because we need to understand what the assumptions underneath our models and our algorithms are. We need to know what their failure modes are, what kind of problems they're good at, what kind of problems they're not good at. And sometimes it can be really tough to do this analysis, right? And so it's obviously going to take a while until we get proper, better interpretations for deep models in a probabilistic sense again. And as David Gley said, there's going to be a workshop about it tomorrow morning. Right? So in the context of sort of historically seeing this in the context of kernel methods, which I find interesting as well, it also took, I think, at least this community quite a while to understand the connection between kernel rich regression and kernel machines in general and their Bayesian interpretations as Gaussian process models. I mean, historically there were other people who were thinking about this earlier, but I think in this community kernels have arrived in the 90s and then Gaussian processes arrived in the mid-2000s. So maybe we'll have to wait 10 years before we got proper Bayesian deep methods, and then they'll become more sample efficient and more robust and better to optimize and better to train, and we'll see our advantages from this here.
So one thing I might want to sort of differentiate between is this idea that Dave Mackay always espoused and that he claimed to have gotten from Steve Gull, which is that the first thing you do ever when you're encountering any kind of modeling problem is you write down the joint probability of all the stuff you can see and all the stuff you can't see and you'd like to model, and once you have that joint probability, then everything else is just turning the crank. Obviously this entire workshop is about turning that crank, so that's a sort of, but it's nevertheless an appealing view of separating out modeling from inference. And so the question of what do we do with Bayesian deep neural networks, where I tend to view that through the lens of representing uncertainty in the weights. And you could do that in a GAN or not. But there's this separate question of like, what's the inductive principle at work in a GAN? And is that something that is satisfying the maximum likelihood principle in some way? And I think there are different opinions about that, and I have not yet formed an opinion on this. But I think that is, to me, that's the question that is really being raised here, which is, what is the joint probability, if we are viewing this through the lens of some joint probability that's being, that's the sort of the hill we're trying to climb, then, how are we getting to that? And the fact that, and it is frankly confusing and interesting that it tends to produce samples that look really good while actually having a worse density estimate, right? And so that tells us a lot of complicated things about the relationship between the maximum likelihood principle and sort of NATS as a way to talk about our work and in AI, and this idea that perception seems not to care at all about NATS, right? In a way, and to me, we're not yet to an understanding of this gap between just how good those things look relative to their actual density estimates. Maybe the answer is that they're just overfitting like crazy in ways we don't yet understand. Maybe it turns out that the maximum likelihood principle is the wrong principle, for at least for certain kinds of problems. I don't think that's probably true, but it'd be nice to close the gap.
I think that question was dancing around a couple issues. One of the issues is the question of what's going on with these alternative objective functions that are out there. The other question was model selection and evaluate the quality of our models. Have any thoughts on, suppose we take the medicine of David Mackay and also Don Rubin, and we write down everything that we see and don't see as a big probability model, and then we turn the crank because we've attended this workshop. What do we do with that? What do we do with the posterior distribution that we've obtained? How do we, if we have a downstream task, how do we evaluate it? If we're trying to do real science or real inferences about the world, try to understand our data through the model, what are the ways that you like to evaluate what you've done when you fit a Bayesian model? But,
well, Dave, posterior predictive checks are a really nice way to do that, for example. I think in general, and this is Dave's work, obviously. I think in general, it's our work. I guess the interesting part about this, again, is that, when you write down the entire joint likelihood of observed and unobserved, you still have this problem of not being able to sort of encode very specific structures. So I mean, in general, in scientific work, I feel like because of the price you pay for having fewer samples and high dimensions, again, you need to make a lot of simplifying assumptions and then test those assumptions very, very explicitly. So model misspecification keeps coming up. And I think the one thing that has come up on this panel a few times is that it's not only model misspecification, but it's also actually what crank you use to turn, right? You have to actually have to think about the fit of the method with the model itself and with the assumptions that you're making and with the goal of the model. Sort of a confusing question, but absolutely model misspecification, also probably inference misspecification, or however you want to say it, is critical to test.
are there other questions from the audience? I have a question while you're thinking. Someone raise their hand. Okay. Oh.
Yeah, just related to what you were just saying, people, I guess, in your situation, you're trying to understand our like the different methods, it seems like they would affect like the type 1 shape where you use like this kind of regularization, you use like this kind of approach, and then a little are there empirical approaches to try to understand those trade-offs? I guess this is still
The question is essentially when you think about sort of the type 1, type 2 type errors that you get from misspecified models, how does that play out? How do you sort of balance the two? I think it's a really good question, but it absolutely, we usually have a goal in terms of the scientific question we're asking, whether it's to actually give a set of hypotheses to a scientific collaborator to evaluate in the lab, in which case, if we have an FDR of 50%, they're going to be really angry at us. There's going to be a lot of bad hypotheses in there, and they're going to spend a lot of money on something that doesn't work. So, I think in general, precision is something that we think very carefully about. But then again, if we're going to do something else, we're going to come up with a set of hypotheses where the experiments are very, very easy. We can use something bulk, and we can have hundreds, thousands of them. Maybe we're just limited in the number. We can go another direction. So I think it sort of depends what the downstream results are used for.
Just a brief follow-up. So we did some work where we tried to estimate how over-complete a representation you'd need to model visual scenes and what the sparsity should be of that model, because that was important for neuroscientists. And that involved running annealed importance sampling for a very long time and a lot of natural scenes data, and we sort back and said, how can we trust the results? So actually most of the work that we did in that paper was training models on natural scenes of various sizes where we'd know what ground truth was, sampling from those models, and then checking that AIS gives back the right over-completeness and the right sparsity. So, it's sort of like a poor man's check, but the generative model, the generative framework does give you a decent way of giving you some faith in what you've got.
Richard, you mentioned earlier the need for theory. something that has struck me for a long time is that while in some subfields of statistics and machine learning there are clear theoretical frameworks inside which to think about methods, we don't have one necessarily for approximate inference. You know, we know MCMC gives us a sample from the posterior if we wait forever, but other than that, you know, it's limited what we know. What kinds of, for any of you, considerations do you think we need to make when we think about forming? I think one of the next things to do is to form a theory, or a framework. What are some of the considerations you think we need to make when we're thinking about that?
I just might point out that I mean there does exist theory for MCMC, right? I mean it is true. It is in practice for most of the models we test like super slow and super hard to understand in any formal way. But there does exist the concept of like a mixing rate, right? And then we get guarantees on convergence over estimators. And there's also the exact sampling literature, right, where you have a provably exact sample from the model. So, however, neither of those things are regularly applicable in the kinds of problems we actually tackle. And from my point of view, a lot of these questions boil down to how do we make that toolbox bigger? And I don't yet have an answer.
Oh, I'm not sure I have an answer, but this is a beautiful question. I totally agree. This is an extremely important question. So, just to sort of hark back a little bit again to this sort of connection to quadrature, but there is actually a theory. So that might be provide a bit of a few pointers for a few sort of areas to take loans from to create something for approximate inference. So in a particular technical sense, we can think of MCMC or MC, exact sampling, Monte Carlo sampling, as a limit case of Bayesian quadrature. I mean, it's a limit case of many things, but it's also a limit case of any quadrature rule, where the interpolation rule is white noise. Right? So you just assume that the only property that the integrand has is that it's integrable. And it's not necessarily continuous, it's not necessarily white. Right? And then there's, in that sort of extrapolation space, or this extrapolation that ends at Monte Carlo can be extended to more interesting models. For example, the next step up in terms of assumptions is the trapezoid rule, which assumes that the integrand is continuous but not differentiable. And it's a particular Gaussian process prior. And then there's sort of a whole family of kernels which create more and more performant quadrature rules, which converge at much higher rates, up to and beyond polynomial rates, at the cost of making stronger and stronger assumptions. So there's a really sort of, this is of course like sort of no free lunch, right? The more prior assumptions your computation makes, the better it performs. And I find this a really sort of, the first time I realized this, this really hit me that Monte Carlo is in a sense the lowest common denominator of everything, right? It's the one algorithm that essentially works on everything, but it also makes horrible prior assumptions that are so vague that you kind of can't expect it to work well. And that's motivated me to think about more advanced methods. But then, of course, immediately this question arises of, well, what is it actually going to work well on? So for methods like, for example, variational inference, this connection is, of course, much harder to make because the loss function is not quadratic, so the analysis is a lot harder. But I think there is kind of an interesting connection that, in the sense that variational inference performs some form of regression in probability distribution space, if you want to call it regression, but minimizing some loss function. The usual variational bounds that we use are sort of similar to parametric regression models, right? So because they're sort of finite dimensional, like unless you have some adaptive way of increasing the number of approximate or the flexibility of Q, right? So if you have that kind of situation in regression, everybody would say, well, if you do linear regression, then you're going to have a hard time, right? It's sort of in terms of guarantees of convergence, there's very little out there. It's sort of the only thing that is actually going to work on is if the true function actually comes exactly from this parametric space. In the same sense that variational inference works exactly if the true P is actually equal to Q, but if they're in the same exponential family. And of course, then you wouldn't do it because then you wouldn't need to do approximate inference in the first place. Right? So, but that's sort of an exciting direction, right? Kind of thinking more about how to create more flexible families of Q, for example, and then try to get a feeling for how in which sense they can be consistent, in which sense their sort of approximation error can be bounded in some sense. is a I think very interesting direction, and the sort of the deep problem will always be that there is a real trade-off between prior assumptions and performance, right? Methods that work really well on some problems are bound to work really badly on many others. And making this kind of trade-off clear and more formal, I think is a really interesting theoretical question.
Let me just sort of like throw a little bit of a twist in this, which is that I articulated a second ago. Also, this I think it's kind of very related. This spectrum from models that we love for which inference doesn't work, all the way up to models that we don't love very much for which we have guaranteed inference procedures. And but it is the case that we all the time write down models for which effectively we have negative results on being able to fit them formally, right? There's this model, latent Dirichlet allocation, I think, that is, that's like unfittable in a formal sense, right? It's like, well, but it's also, it's NP hard or something, right? And and so inference is one thing, but we're never going to make progress unless we either develop an approximation theory that's like robust for these very, very hard models, or we come up with model classes that are not sort of just full of negative results, for which we can never expect to do inference. Like there's all of these inference methods that we like to use in sort of deterministic settings collapse on solving optimization problems, and if that optimization problem corresponds to, could in the limit of some parameters be a satisfiability problem or something like that, then we're screwed, right? Like there's no, we need to rethink what we're asking these methods to do.
So to put a sort of applied spin on it too, we have, I'm thinking about MCMC, there was a model described, which is essentially a very long and glorified HMM. It was actually fit with Gibbs sampling for a specific genetics application. The way that they ran Gibbs sampling was essentially by running it 30 times. And that sort of reproducibly, it obviously is not sampling from the posterior, but it actually produced incredibly robust solutions, and no one knows why. And I feel like early stopping and sort of things like this, which actually tend to work really well in practice too, and I'm sort of drawing on also a huge body of recent work from Mike Jordan's group and others, thinking about sort of, you have sort of a limited expense account for computation or time. What can you say about the answers and how bad could they possibly be? And really making sure that we know what the guarantees are on that.
So I don't have much to add, apart from the fact that I think it's important we keep breaking off little pieces of theory for models and inference algorithms and sort of adding to this mix of theory that we have. And I wanted to plug Guillaume's work on EP, who has the first sort of asymptotic analysis of EP, VB, and comparing that to Laplace. I think it's sort of the first theoretical chunk that we have for the EP algorithm. Hopefully that will bring statisticians to our community to add to that body of literature.
Great set of answers. I think what I heard too was that the theory we need is about characterizing the trade-offs that we necessarily make when we're solving problems, trade-offs around speed and accuracy, of course. So we have time for one more question.
Yeah, just to follow up on that, I mean, to what extent do you think that some of the difficulty in having theoretical or what the guarantees is related to the focus on just the inference problem, especially the approximate inference problem, but without considering the potential distinct problems that go alongside that?
Yeah, I mean, I totally agree with that. That's sort of how I started off. I think you have to, if you're doing approximate inference, fold the task into the application into the analysis. So I think we should be evaluating our methods in the context of some of the most successful places where approximate inference has been deployed. I guess probabilistic numerics will become such a field, Bayesian optimization, active learning, and sort of drive the development through exceptional results in those areas that are well suited to approximate inference.
I mean, to that end, I mean, I think this is a huge thing that we don't have a good answer to. We were talking about David McKay earlier, and this, I'm going to write down the joint probability distribution, and then I'm going to turn the crank on that. That assumes kind of that there's actually two cranks, right? Like the first crank, you write down your model, and then you turn the crank to do inference. But then there's this implied, decision that you're going to layer on top of that, right? That involves integrating over almost certainly some subset of the variables you just spent a lot of time estimating. And there's a kind of version, I think, of like bounded rationality in which we should take seriously the fact that we only have a limited budget of computation, and that maybe we want that computation to focus on the actual estimators that are going to matter. And I know Simon Lukasz-Julian, if he's here, and Zubin Garamani had done a little bit of work on this, but I think it's something that deserves a lot more attention. I don't know, Amos, have you done this too?
Yeah, I was wondering whether Simon was here as well. The thing that came to my mind, Amos, when you brought this up, is that, of course, usually then the decision, so here, this problem is right that we have this interactable computation to do, and then we approximate it with some approximate computation. Now, annoyingly, the decision problem afterwards, of course, will also involve some intractable computation. So you'll optimize some loss function, and then it's going to be an optimization, or maybe something more complicated, right? Maybe some dynamical prediction that involves solving differential equations and then optimizing some parameters to control some whatever. So I think there's really this is actually an area where I think there's a limit to how much theory can do for us, and it will have to conform with the more practical decisions that we as a community make on our software design as well. So if we decide that we're going to have a little gray box or black box even that does optimization for some loss function, and a little black box that gives us the loss function, and the black box that does the inference and so on, then that doesn't mean that it's impossible to take all of these connections into account, but there will have to be a language for these black boxes to talk to each other. Right? Of course, I'm going to plug once again that language should be probability measures, and it should be message passing between algorithms rather than within a model. Other people might have other opinions, of course. But it would have, as Ryan said, I think there's sort of a bounded rationality thing going on, and it's even a bounded community acceptance thing going on, that we could have the most beautiful theory for how everything interacts with everything, and people are just not going to be able to make practical use of it because we will rely on our existing toolboxes or sort of developing toolboxes. So I find it interesting to think about what sort of a common set of language could be that allows algorithms to talk to each other and find out if one of them is doing the wrong thing in the context of what the others are trying to do. Maybe just to follow up, I think one big opportunity from probabilistic programming, not only does it empower people who are not experts necessarily in approximate inference to use these things, it also gives us a chance to collect data about how well the approximate inference methods that they've used for their particular model actually work, and to use that to feed back into the loop. So maybe we should have an eye on that as we develop these tools which we're pushing out to people, a way to get feedback and to really figure out what they're doing and what approximate inference algorithms actually work for the particular models that people are interested in.
Great, that's a great point to end on. So Philip, Ryan, Barbara, and Richard, thanks very much for this lively discussion.